2.1. The conduction rate equation. Although the conduction rate equation, Fourier's law, was introduced in section 1.2, it is now appropriate to consider its origin. Fourier's law is phenomenological. That is, it is developed from observed phenomena rather than being derived from first principles. Hence, we view the rate equation as a generalization based on much experimental evidence. For example, consider the steady-state conduction experiment of Figure 2.1. A cylindrical rod of known material is insulated on its lateral surface, while its end faces are maintained at different temperatures, with T1 greater than T2. The temperature difference causes conduction heat transfer in the positive x direction. We are able to measure the heat transfer rate, Q sub x, and we seek to determine how Q sub x depends on the following variables: delta T, the temperature difference, delta x, the rod length, and A, the cross-sectional area. We might imagine first holding delta T and delta x constant and varying A. But if we do so, we find that Q sub x is directly proportional to A. Similarly, holding delta T and A constant, we observe that Q sub x varies inversely with delta x. Finally, holding A and delta x constant, we find that Q sub x is directly proportional to delta T. The collective effect is then that Q sub x is proportional to A times delta T over delta x. In changing the material from, say, metal to plastic, we would find that this proportionality remains valid. However, we would also find that for equal values of A, delta x and delta T, the value of Q sub x would be smaller for the plastic than for the metal. This suggests that the proportionality may be converted to an equality by introducing a coefficient that is a measure of the material behavior. Hence, we write Q sub x equals K times A times delta T over delta x. And that was a lowercase k, which is the thermal conductivity, and it's measured in watts per meter Kelvin. It's an important property of the material. Evaluating this expression in the limit as delta x approaches 0, we obtain for the heat rate Q sub x equals negative lowercase k times A over differential T over differential x. And for the Ux, we divide by A, get another equation that's the same thing. Recall that the minus sign is necessary because heat is always transferred in the direction of decreasing temperature. Fourier's law, as written in equation 2.2, implies that the heat flux is a directional quantity. In particular, the direction of Q sub x double prime is normal to the cross-sectional area A. Or more generally, the direction of heat flow will always be normal to a surface of constant temperature called an isothermal surface. Figure 2.2 illustrates the direction of heat flow, Q double prime sub x, in a plane wall for which temperature gradient dt dx is negative. From equation 2.2, it follows that Q double prime sub x is positive. Note that the isothermal surfaces are planes normal to the x direction. Recognizing that the heat flux is a vector quantity, we can write a more general statement of the conduction rate equation, Fourier's law, as follows. Q double prime, bold, that's vector, equals negative k, I think this is bold, gradient, or nabla, or del t. So negative lowercase k, nabla t, and that's the gradient, so that's increasing, maximum increase, direction of maximum increase, which is just the partial of t with respect to x, y, and z, times the unit vectors I, j, and k, and all of that times negative k. Where, as I'm continuing with the reading now, where upside down delta is the three-dimensional del operator and t of x, y, and z is the scalar temperature field. It is implicit in equation 2.3 that the heat flux vector is in a direction perpendicular to the isothermal surfaces. An alternative form of Fourier's law is therefore Q double prime sub x equals negative k dt dn, partial t, partial n, times bold n. And in figure 2, it says with this wall, with the temperature shown decreasing from left to right as Q flows from left to right, it says the relationship between coordinate system, heat flow direction, and temperature gradient in one dimension. So take a look. And then there's a curved surface with some vectors, the Q sub x, Q sub y, and then the resultant vector. We're continuing reading where Q double prime sub n is the heat flux in a direction n, which is normal to an isotherm, and that's a place where it's constant temperature. And bold n, that might be a nu, is the unit normal vector in that direction. I think it's just regular lowercase n. This is illustrated for the two-dimensional case in figure 2.3. The heat transfer is sustained by a temperature gradient along bold n. Note also that the heat flux vector can be resolved into components such that, in Cartesian coordinates, the general expression for Q double prime is Q double prime times, ijk, bold ijk, times Q sub x double prime plus Q sub y double prime plus Q sub z double prime. We're in equation 2.3, it follows, okay, all of these same equations, but the first one, it goes for Q double prime sub x, y, and z, and it's Q double prime sub x equals negative k times partial t over partial x. I won't read the rest. Continuing reading, each of these expressions relates the heat flux across a surface to the temperature gradient in a direction perpendicular to the surface. It is also implicit in equation 2.3 that the medium in which the conduction occurs is isotropic. For such a medium, the value of the thermal conductivity is independent of the coordinate system. Doesn't matter which way you go. Fourier's law is the cornerstone of conduction heat transfer, and its key features are summarized as follows. It is not an expression that may be derived from first principles. It is instead a generalization based on experimental evidence. It is an expression that denotes probably is what this word might mean. Denotes. Never seen that one. Yay, learning. An important material property, the thermal conductivity. In addition, Fourier's law is a vector expression indicating that the heat flux, the word's bothering me, is normal to an isotherm and in the direction of decreasing temperature. Finally, note that Fourier's law applies for all matter, regardless of its state, solid, liquid, or gas. And define. Somebody is singing outside. A veil, especially a deep, narrow, would it? Excuse me, so sorry. How much time do we have? I don't have much personally, but I will. Let's see, 2.2. Do I have time to go through this? I don't. 2.2.2. Let's continue just a couple minutes. The thermal properties of matter. To use Fourier's law, the thermal conductivity of the material must be known. This property, which is referred to as a transport property, provides an indication of the rate at which the energy is transferred by diffusion process. It depends on the physical structure of matter, atomic and molecular, which is related to the state of the matter. In this section, we consider various forms of matter, identifying important aspects of their behavior and presenting typical property values. 2.2.1 Thermal conductivity. From Fourier's law, equation 2.6 is the thermal conductivity associated with conduction in the x direction is defined as K sub x equals negative Q double prime sub x over parentheses dt dx, or partial t partial x, end parentheses. Similar definitions are associated with the thermal conductivities in the y and z directions, K sub y, K sub z. But for an isotropic material, the thermal conductivity is independent of the direction of the transfer. K sub x equals K sub y equals K sub z is the definition of K. From the foregoing equation, it follows that for a prescribed temperature gradient, the conduction heat flux increases with increasing thermal conductivity. In general, the thermal conductivity of a solid is larger than that of a liquid, which is larger than that of a gas. As illustrated in figure 2.4, the thermal conductivity of a solid may be more than 4 orders of magnitude larger than that of a gas. This trend is due largely to differences in intermolecular spacing for the two states. The solid state. In the modern view of materials, a solid may be comprised of free electrons and atoms bound in periodic arrangement called the lattice. Accordingly, transport of thermal energy may be due to two effects: the migration of free electrons and lattice vibrational waves. When viewed as a particle-like phenomenon, the lattice vibration quanta are termed phonons. Cool word, right? Write it down. In pure metals, the electron contribution to conduction heat transfer dominates, whereas in nonconductors and semiconductors, the phonon contribution is dominant. Kinetic theory yields the following expression for thermal conductivity: K equals 1/3 capital C times lowercase c bar times lambda lowercase mfp, where mfp should probably be mean free path. For conducting materials such as C, defined as C sub E, is the electron-specific heat per unit volume. C bar is the mean electron velocity, and lambda MFP is defined as lambda sub E is electron mean free path, which is defined as the average distance traveled by an electron before it collides with either an imperfection in the material or with a phonon. In non-conducting solids, C is defined as C sub pH, which is the phonon-specific heat. C bar is the average speed of sound, and lambda sub MFP is defined as lambda sub phonon, pH. Is the phonon mean-free path, which again is determined by collisions with imperfections or other phonons. In all cases, the thermal conductivity increases as the mean-free path of the energy carriers, electrons or phonons, is increased. When electrons and phonons carry thermal energy leading to conduction heat transfer in a solid, the thermal conductivity may be expressed as K equals K sub E plus K sub pH. The first approximation, K sub E, is inversely proportional to the electrical resistivity, ρ sub E. For pure metals, which are low ρ sub E, Ke is much larger than Kph. In contrast, for alloys, which are of substantially larger ρ sub E, the contribution of K sub pH is no longer negligible. For nonmetallic solids, K is determined primarily by K sub pH, which increases as the frequency of interactions between the atoms and the lattice decreases. The regularity of the lattice arrangement has an important effect on K sub pH. With crystalline, that is to say, well-ordered, materials like quartz having a higher thermal conductivity than amorphous materials like glass. In fact, for crystalline nonmetallic solids such as diamond and beryllium oxide, K sub pH can be quite large. Exceeding values of K are associated with good conductors such as aluminum. The temperature dependence of K is shown in figure 2.5. for representative metallic and nonmetallic solids. Values for selected materials of technical importance are also provided in Table A.1, metallic solids, and Tables A2, A3, nonmetallic solids. More detailed treatments of thermal conductivity are available in the literature. The solid state, micro and nanoscale effects. Pop quiz, what's micro? What's nano? All right, 6 and 9, right? In the preceding discussion, the bulk thermal conductivity is described, and the thermal conductivity values listed in Table A1 through A3 are appropriate for use when the physical dimensions of the material of interest are relatively large. This is the case in many commonplace engineering problems. However, in several areas of technology, such as microelectronics maybe, the material's characteristic dimensions can be on the order of micrometers or nanometers, in which case care must be taken to account for the possible modifications of K that can occur as the physical dimensions become small. Cross-sections of LMS. The same material having the thickness L1 and L2 are shown in figure 2.6. Electrons or phonons that are associated with the conduction of thermal energy are also shown qualitatively. Note the physical boundaries of the film act to scatter the energy carriers and redirect their propagation. For large L over lambda, the effect of the boundaries on reducing the average energy carrier path lengths is minor, and conduction heat transfer occurs as described for bulk materials. However, as the film becomes thinner, the physical boundaries of the material can decrease the average net distance traveled by the energy carriers, as shown in figure 2.6b. Moreover, electrons and phonons moving in the thin x direction, representing conduction in the x direction, are affected by the boundaries to a more significant degree than energy carriers moving in the y direction. As such, for films characterized by small L over lambda MFP, we find that K sub x is less than K sub y is less than K, where K is the bulk thermal conductivity of the film material. For L over A sub MFP is for L over A that are greater than or equal to 1, the predicted values of K sub x and K sub y may be estimated to within 20% from the following expression. Wow, that's a rough estimate. K sub x over K equals 1 minus lambda MFP over 3L. K sub y over K equals 1 minus the other 2/3. 2 lambda MFP over 3 pi L. 3 pi L. Interesting. Okay, got a pi thrown in there. Very interesting. Very weird. Alright, I guess it's not weird. Must be a tube or something. In equation 2.9a, B reveal that the values of K sub x and K sub y are within approximately 5% of the bulk thermal conductivity if L over A MFP is greater than 7 for K sub x and L over A lambda, did I say A? L over lambda MFP is greater than 7 for K sub x and L over lambda MFP is greater than 4.5 for K sub y. Values of the mean free path, as well as critical film thicknesses below which microscale effects must be considered, L-crit, are included in Table 2.1 for several materials at T approximately at around 300 kelvins. For films with lambda MFP less than L, less than the critical, for those, K sub x and K sub y are reduced from the bulk value as indicated in equations 2.9 A and B, the ones I just mentioned, the one where the second one had pi in there. No general guidelines exist for predicting values of the thermal conductivities for L over lambda MFP less than 1. Note that in solids, the value of lambda MFP decreases as the temperature increases. In addition to scattering from physical boundaries, as in the case of figure 2.6b, energy carriers may be redirected by chemical dopants embedded with a material or grain boundaries that separate individual clusters of material in otherwise homogeneous matter. Nanostructured materials are chemically identical to their conventional counterparts, but are processed to provide very small grain sizes. This feature impacts heat transfer by increasing the scattering and reflection of energy carriers at grain boundaries. Measured values of thermal conductivity of a bulk nanostructured yttria-stabilized zirconia material are shown in figure 2.7, and I assume yttria stabilized means it's stabilized with yttrium, the element on the periodic table. Maybe not, but that's my guess. This particular ceramic is widely used for insulation purposes in high-temperature combustion devices. Conduction is dominated by phonon transfer, and the mean free path of phonon energy carriers is, from table 2.1, lambda sub MFP equals 25 nanometers at 300 kelvins. As the grain sizes are reduced to characteristic dimensions less than 25 nanometers and more grain boundaries are introduced in the material per unit volume, significant reduction of thermal conductivity occurs. Extrapolation of the results from figure 2.7 to higher temperatures is not recommended, since the mean free path decreases with increasing temperature, and grains of the material may coalesce, merge, and enlarge at elevated temperatures. Therefore, L over A MFP becomes larger at higher temperatures, and reduction of K due to nanoscale effects becomes less pronounced. Research on heat transfer in nanostructured materials continues to reveal novel ways engineers can manipulate the nanostructure to reduce or increase thermal conductivity. Potentially important consequences include applications such as gas turbine engine technology, microelectronics, and renewable energy. Tell me more about this one, renewable energy. All right, I'll have to look at that. 8. The fluid state. The fluid state includes both liquids and gases. Both the intermolecular spacing is much larger and the motion of the molecules is more random for a fluid state than for the solid state. Thermal energy transport is less effective. The thermal conductivity of gases and liquids is therefore generally smaller than that of solids. The effect of temperature, pressure, and chemical species on thermal conductivity of a gas may be explained in terms of kinetic theory of gases. From this theory, it is known that the thermal conductivity is directly proportional to the density of the gas, the mean molecular speed, c bar, and the mean free path, lambda sub mfp, which is the average distance traveled by an energy carrier, that is, a molecule, before experiencing a collision, kaboom. K is around 1/3 of c sub v times rho times c bar times lambda sub mfp. And for an ideal gas, we throw in a bit more in a square root. That is to say lambda. I guess we're just solving for lambda here. Is that what's... All right. Lambda 1/3. I'll just read it. Lambda mfp equals k sub capital B times t over root 2 times pi times d squared times p. The kb is the Boltzmann constant. That is 1.381 times 10 to the negative 23rd. 6.022, and that's Avogadro's, and now 1.381. 1.381. How do you remember that? I don't know. D is the diameter of the gas molecule, representative values of which are included in figure 2.8. P is pressure. As expected, the mean free path is small for high pressure or low temperature, which causes densely packed molecules. The mean free path also depends on the diameter of the molecule, with larger molecules more likely to experience collisions than smaller ones. In the limited case of an infinitesimally small molecule, the molecules cannot collide because they're not there. They're just fake points, resulting in an infinite mean free path. Yeah, are we forgetting about the wall? Anyways, the mean molecular speed, c bar, can be determined from the kinetic theory of gases, and equation 2.10 may ultimately be expressed as a larger equation, which isn't worth reading. You have to look at this, open your book or look at the screen. Where the parameter gamma, I'm going cross-eyed, sorry, I think it's a gamma. Lowercase gamma is the ratio of the specific heats, gamma equals Cp over Cv. And squiggly n is Avogadro's number, 6.022 times 10 to the 23rd molecules per mole. Hey kitty. Equation 212 can be used to estimate the thermal conductivity of gas, although more accurate models have been developed. It is important to note that the thermal conductivity is independent of pressure except in extreme cases, as, for example, when conditions approach that of a perfect vacuum. Therefore, the assumption that K is independent of gas pressure for large volumes of gas is appropriate for the pressures of interest in this text. Accordingly, although the values of K presented in Table A4 pertain to atmospheric pressure or saturation pressure corresponding to the prescribed temperature, they may be used over a much wider pressure range. Molecular conditions associated with the liquid state are more difficult to describe, and physical mechanisms for explaining the thermal conductivity are not well understood. The thermal conductivity of nonmetallic liquids generally decreases with increasing temperature. As shown in figure 2.9, water, glycerin, and engine oil are notable exceptions. The thermal conductivity of liquids is usually intensive to pressure except near a critical point. Also, thermal conductivity generally decreases with increasing molecular weight. Values of the thermal conductivity are often tabulated as a function of temperature for the saturated state of the liquid. Tables A5 and A6 present such data for several common liquids. Liquid metals are commonly used in high heat flux applications, such as in nuclear power plants. The thermal conductivity of such liquids is given in Table A7. Note that the Note that the values are much larger than those of the non-metallic liquids. For obvious reasons, will have to come back to this, but that should have been a good chunk of time. Does it say anywhere here? All right, I will see you later and continue from there.